Greetings and welcome to the video introduction to the Chemistry 221 Lewis Structures Lab. Lewis structures are fascinating ways that chemists can keep track of where electrons reside in molecules. And from an understanding of a Lewis structure, you can tell, for example, where a molecule is most likely to be attacked by another molecule. You can tell the parts of the molecule that are more into electrons or less into electrons, as it might be, and lots of other things. Plus, you can actually understand why molecules take on various shapes. And the fundamental thing that drives all of the geometry differences is that electrons don't want to be around electrons. Electrons and electrons repel. So use that as we go through the Lewis structure and apply its related VSEPR geometry to molecules. Lots of cool things you can do. So without further ado, let's check out what Lewis structures offer the chemist and how you can create your own. Lewis structures allow a chemist to visualize really how electrons are placed around some kind of central atom. And Lewis structures, which was developed by G.N. Lewis, a cool chemist, really helpful to scientists because in addition to being able to show where the electrons are, it gives information about the geometry, bond angles, and polarity of the molecule if you also apply what is called the valence shell electron pair repulsion theory. And of course, that's way too many syllables for lazy chemists to use, so let's just call it VSEPR, all right? And VSEPR is actually a pretty cool extension of Lewis structures. So you're going to draw a lot of Lewis structures in this lab, and then you're going to apply the VSEPR rules just to kind of get used to them. And while you're doing this lab, I cannot emphasize enough that you either have a digital copy or a physical copy of what I call the Geometry and Polarity Guide. And it's in the companion and it's online. There's a direct link right there, mhchem.org/GOPO. Anyway, that will give you this Geometry and Polarity Guide. It's about 4, 5, 6 pages long. I think it's 5 pages actually. But anyway, interpreting that will make your life a lot easier. So you'll draw the Lewis structure first and then interpret it using the Geometry and Polarity Guide. At this point, I hope that you've viewed the lectures for this material online already, so Lewis structures aren't like totally a foreign idea. But just to make sure we're all on the same page, when you're drawing a Lewis structure, I do recommend these 5 steps you go through. And the first is just to decide what the central atom is. And most of the time, the first atom listed is the central atom, but there's a couple ways you can do even better. The central atom is technically the atom of lowest electronegativity. And in the lower left-hand corner there is the chart of electronegativity values. Fluorine is the most electronegative, followed by oxygen, nitrogen, and chlorine, etc., etc. So this central atom, most of the time, is the atom of lowest electronegativity. On the other hand, it can never be hydrogen. Hydrogen doesn't have the electron structure, if you will, to handle more than a single bond. So it can be a terminal atom, which means an atom on the outside of the molecule, but it cannot be a central atom. It can only handle one bond. Now, the next thing you want to do is count the number of valence electrons, and I would recommend converting them to electron pairs. So valence electrons equal the group number. So carbon is group 4. That means it has 4 valence electrons. And phosphorus is group 5, so it has 5 valence electrons. Once you have the total number of electrons, the valence electrons, I would divide that number by 2 in order to find out how many electron pairs you have. We're going to be distributing the electrons as pairs, either bonding pairs or lone pairs, and so most of the time you want to figure out how many pairs you have to deal with. Now, the first thing in step 3 to when you're building the molecule is you have to connect the central atom to the outside atoms. So you do that by forming sigma bonds, which is nothing more than a single bond between the central atom and the surrounding atoms. That keeps the outer atoms connected to the inner atoms. One of those sigma bonds, by the way, is a pair of electrons. So subtract that from your total. And if you have electrons left over, you put them as lone pair electrons first around the outside atoms, and then if you have any left over, you put them on the inside. Most of our molecules will obey the octet rule, which means 4 pairs, but as we talked about in lecture, not all of them will, and period 3 and lower can go outside the octet rule. However, almost all the biochemistry and organic chemistry things do follow the octet rule, so we'll be definitely using that quite a bit. Finally, if an atom or atoms does not have an octet, you have to create double bonds, pi bonds, all right? And you use a lone pair on one of the adjacent atoms to do that. I'll show you an example of how that works here in a little bit. Atoms like carbon, nitrogen, oxygen must have an octet, no exceptions. So if carbon only has like 3 pairs around it, it needs the 4th pair to get an octet. It will actually force one of the outside atoms to share its lone pair, making like a pi bond or a total of a double bond. I'll show again this here in a little bit. When you're ready to use VSEPR rules, all right, again, I do recommend using that geometry and polarity guide, and you can see it listed down there. Now, if you look at the geometry and polarity guide, first of all, on the far left, it'll state how many clouds there are. And a cloud is a reference to electrons in pairs, literally being a cloud. If it's a lone pair, it's a cloud on one atom. On the other hand, if you have a bond, it would be an electron cloud between 2 atoms. Now, one thing we'll talk about here in a little bit is that if you have a single, double, or triple bond, all of those count as one cloud. So a double bond does not count as 2 clouds. A double bond counts as just 1 cloud, and a triple bond is 1 cloud, etc., etc. So you want to count the number of clouds around the central atom. And once you have that, then you can see even from the description page right there, there's a couple entries for 2 clouds. Then you go into 3 clouds. Eventually you hit 4, 5, and 6 clouds. If you look under 3 clouds, you can see that the first entries have 3 atoms connected, 3 clouds connected to atoms. But then you have 2 atoms connected to clouds and 1 lone pair. And it kind of does this. This is kind of the pattern this thing follows. So you want to find out then of your clouds how many are connected to atoms, and that's the number of atoms. So you can see there under 3 clouds in the lower left-hand corner, when you go towards the bottom, 3 clouds, 2 atoms, 1 electron pair is one of them, and the next one's even 3 clouds, 1 atom, 2 electron pairs. So notice that atoms plus electron pairs equals numbers of clouds, and you just want to find out which one you have. So literally the number of atoms connected to your central bond, that's going to be the number of atoms, all right? There is also a symmetric and asymmetric, and we'll see examples of this more in the lab, but if you have a symmetric atom, then everything around the central atom is the same, or at least there's atoms at 180 degrees that cancel each other out, that kind of thing. Most molecules are asymmetric, which means that not everything is the same around the central atom. So if you look, for example, there at CO2, which is the first example, CO2 would be a symmetric molecule because everything around the carbon is the same. You have a double bond on the left and a double bond on the right. COS, all right, which is similar to carbon dioxide, is not symmetric. It would be asymmetric because on the carbon you have an oxygen on the left and a sulfur on the right, so not everything is the same. BF3 is symmetric. Everything around the boron is the same, but as you can probably see, the next one, COH2, that one would be asymmetric. Everything around the central atom's not the same. So hopefully you can begin to kind of see what's happening. Symmetric and asymmetric helps with polarity. Once you find the right number of clouds and you figure out how many atoms and electron pairs there are, and you make a guess at least as to what symmetric and asymmetric are, you can literally just read left to right and you'll find electron pair geometry, the name, the molecular geometry, the name, bond angles, polarity. So literally it's just copying down that particular row to figure it out. So it's worth your time to kind of figure this out. So what I'd like to do now is do some examples of how this works out and show you that it's hopefully pretty chill. And I'll try to do not only the Lewis structure, and then I'll also try to interpret it in terms of the other things. The first example I'd like to do is for CH4. CH4 is a compound called methane, all right? Methane we'll talk about more in a later lecture. But the first thing you want to do is just count up valence electrons. By the way, carbon is the only atom here that can be the central atom. Hydrogen can't be central, so it kind of has to be carbon. So we're going to put carbon in the middle. Carbon has 4 valence electrons, and hydrogen in group 1 has has 1, but there's 4 hydrogens, so that means there's a total of 8 valence electrons, or if we divide this by 2, that means there's going to be 4 pairs of electrons, all right, and that's going to be important. Carbon is the central atom because hydrogen cannot be. Also, carbon is the first atom listed, and most of the time, not all the time, but most of the time, that's a good indicator as what the central atom is. I'll place the other atoms around the central atom. So I'm going to place the hydrogens just around them like that. Now, initially, the hydrogens would float away, so I create a bond between the outer atoms and the inner atoms. That's called a sigma bond or a single bond, and we'll talk more about what that means in a little bit. But the important thing is that each one of those lines I just drew is an electron pair. Those are all called bonding pairs. So I had 4 pairs. I just put down 4 on that structure, so you can see I have no pairs left. So this thing right here is the Lewis structure, all right? And it doesn't have to be fancy. You can see that mine's pretty sloppy, all right? A little bit of technology sloppiness too, but anyway, I'm not an artist. Anyway, long story short, this is the Lewis structure for CH4. So pat yourself on the back if you're following along and you got this structure. Woohoo, we're good to go. Now, let's go a little bit further and interpret this molecule for Vesper. Now, in Vesper, you look at the central atom, which in this case is carbon, and carbon has 4 bonds around it, and each of those bonds is a cloud. This would be a 4 cloud system, and there are 4 atoms connected to the central atom, no lone pairs. So if you look at this, and by the way, it is symmetric because everything around the carbon is the same. Those are all hydrogens, all right? If I had 1 chlorine, it would be asymmetric, but this one is symmetric. So if you look at the place where it says 4 clouds, 4 atoms, no electron pairs, maybe symmetric, then the electron pair geometry, or EPG, that's tetrahedral. The molecular geometry, Mg, is also tetrahedral. If there are no lone pairs around the central atom, the electron pair geometry and the molecular geometry are going to be the same. It also asks about bond angles. And if you have a tetrahedral electron pair geometry, that means it's going to be 109 degrees. You can put 109.5, that's okay, but about 109 is totally fantastic. And finally, because everything around the central atom is the same, this molecule is going to be non-polar. Because again, everything around that carbon is the same, just hydrogens. If we had even 1 chlorine or 1 lone pair or 1 uranium or whatever, that would be enough to make this molecule polar. But in this example, yeah, this one's definitely going to be nonpolar because everything around this is the same. Now, this is your instructor's cheesy hand-drawn version. I'm now going to show you a computer-generated version, hopefully in case my drawings are weird, and maybe I missed something too. So this is my computer-generated version. Down here in the bottom, you can see the entry from the Geometry Polarity Guide. We looked for something with 4 clouds. They were 4 atoms, no electron pairs, and everything around the central atom was the same, so it's symmetric. So you can see if you go left to right, the electron pair geometry, which is also known as Vesper geometry sometimes, is tetrahedral. The molecular geometry, or sometimes the shape geometry, molecular shape, that's also tetrahedral. The bond angles, about 109, 109.5 is awesome, and the polarity here, non-polar, because everything is the same around the central atom. Now, a Lewis structure does not have any indication of geometry by default. So my drawing on the last slide was kind of like this one on the top, and it looks flat, okay? But what's cool about VSEPR, and what's good for chemists, because chemists aren't artists, is that you can interpret that carbon as having the 4 bonds around it, as having tetrahedral, and this molecule is not flat. So the second picture right there is what it quote unquote looks like in space. It's not a 2-dimensional molecule, which is what a Lewis structure shows, but it is 3-dimensional. It's got the 3 little points on the bottom and 1 little point on the top, whatever. This is the importance of VSEPR. No one assumes that a scientist can draw, okay? Maybe that's a bias, I don't know, but no one assumes by default that you can draw, and I certainly can't draw worth anything, okay? So the Lewis structure is just way to show where the electrons are around the central atom, and then you can use VSEPR kind of in your mind, if you will, a little bit, and realize it's going to look a lot more like this one than it will the one on the top. But again, your Lewis structures can be flat like that, and that's not a big deal. So if you can do this problem, you've got this lab down, all right? You really do, because this is what we're going to do. We're just going to figure out number of electron pairs and figure out central atom and put them all together. The pictures don't have to be pretty, and then we can use VSEPR and the hopefully helpful geometry and polarity guide to figure out the rest of it. Let's look at a second example. This one's going to be CH2O, okay? This compound actually has the name formaldehyde or methanol, and we'll talk about that later, but that's not important right now. What we want to do is we want to draw this Lewis structure. So if you look at CH2O, all right, usually the first atom listed will be the central atom, and carbon is usually a good bet, by the way, for central atoms. It wouldn't be hydrogen, because hydrogen can only be on the outside, and oxygen is actually one of the higher electronegativity atoms on the periodic table, and oxygen rarely goes on the inside. Between carbon and oxygen, carbon should have a smaller electronegativity. Carbon will definitely be on the inside here, and oxygen on the outside. So carbon's going to be in the middle, and if you want, you can do these in different order. Carbon is going to be in the middle, and we'll put the other atoms just around. And again, you can put them any way you want, because Lewis structures don't have any information as to geometry and stuff like that. We need to figure out the number of valence electrons. Carbon is in group 4, so it has 4 valence. Hydrogen is 1, and there's 2 of them, and oxygen is group 6, so there's 6 valence electrons. So 4 plus 2 plus 2, this is going to be 12 valence electrons, or if you divide it by 2, that means 6 pairs. So back to the structure. Carbon in the middle, the H's and the O on the outside. First thing to do, connect the outer atoms to the inner atoms. So those 3 lines I've drawn right there are each bonding pairs. That's 3 of my 6 pairs. So if I subtract 3, that means I have 3 pairs left. Now, in the last example, we were done, but in this example, what we're going to do with these remaining 3 pairs is we're going to fill in the outer atoms with an octet first, and octet means 4 pairs. And if there's any left over, we'll put them on the central atom. So oxygen likes to have an octet, and an octet means 4 pairs. The pairs can be bonding pairs or lone pair. Right now, the oxygen only has 1 bonding pair to carbon, so we can have 1 lone pair there, a second lone pair there, and a third lone pair there. And that actually uses up the rest of my electrons, so I have no more pairs of electrons left. At this point, you need to look at the diagram we just drew and see if everybody is happy, okay? Now, happy is a very strange word, possibly as a science to use here, but happy means, for example, hydrogen has 1 bond and 1 bond only, and they do, and you want to see if the other atoms have an octet. Now, most of the atoms must have an octet. Some of them can go under, so we saw that boron, beryllium, aluminum can go under sometimes, and some of them can go over an octet. So period 3 and lower atoms can have more than an octet. But carbon and oxygen are certainly period 2. They're going to need to have an octet. Your oxygen right now has 3 lone pairs and a bonding pair. That's 4 pairs total. Oxygen does have an octet, so it's okay. But carbon here has 1, 2, 3 pairs around it. And carbon, like oxygen, must have a 4th pair. So at this point, carbon needs more electron density around it. So what carbon does is it basically forces oxygen to get rid of a lone pair, like let's say it got rid of that one, and make a second bond between the 2 atoms. This second bond is called a pi bond. The first bond you draw is a sigma bond, and the second one is pi. A sigma plus pi makes a double bond. So we would describe the carbon-oxygen bond as a double bond having 1 sigma and 1 pi. Now carbon likes this because now carbon has 4 bonding pairs, 2 single bonds to hydrogen and a double bond to oxygen. That's 4 bonds total. Cool. Oxygen actually is still happy with this as well because oxygen still has 2 lone pairs and it has a double bond, which is 2 bonding pairs to carbon. So it has 4 pairs total. It just has to share a little bit more with carbon than it did before. So this is a good Lewis structure. Everything's got the octet. Hydrogen's happy with just 1. Oxygen on the middle and the outside because it's more electronegative than carbon. So the Lewis structure here, good to go. Let's interpret this now using VSEPR rules. And what we do is you look around this central atom, which is going to be carbon, and you want to count the number of clouds. Okay, so carbon has 1, 2 clouds to hydrogen. So this is a cloud right here, and that's a cloud right there. It also has a double bond. And if you remember from earlier, double bonds and triple bonds as well count as one big cloud. So there are 3 things I circled there. That means there are 3 clouds around carbon. All of the clouds are connected to atoms. There's no lone pairs on the molecule. And if you look on the VSEPR geometry polarity handout there, 3 clouds connected to atoms, 3 atoms, no lone pairs, and also asymmetric because this carbon has different things around it. H's and O's are different from each other. So for this molecule, what I would say is the electron pair geometry is with 3 clouds. It's going to be trigonal planar. And if you want to abbreviate that trig plane, something like that, that's totally fine. Don't call it just trig though, because there's also a trigonal pyramid and a trigonal bipyramid, lots of trig uses. Don't call it planar just either, because there's a trig planar and also a square planar you'll see later. So you have to call it trig plane or trig planar or something like that. You can't get away any less than that. Trust me, I've tried. I'm the lazy chemist. Anyway, babbling. EPG, trigonal planar, when there's 3 clouds around something. Molecular geometry is also going to be trigonal planar because, again, there's no lone pair electrons around carbon, and if that's the case, no lone pairs around the central atom, EPG and MG are going to be the same. Around the trigonal planar electron pair geometry, the bond angles are more like 120 degrees. So those angles, the HCH and the HCO angles, those are all going to be about 120 degrees. And then finally, because this is an asymmetric molecule, not everything is the same around that carbon. That means this molecule is going to be polar, okay? So we made a double bond there because carbon must have an octet, 4 bonds around it. And we can interpret all of this. Just remember in VSEPR, a double bond counts as 1 cloud, just like a triple bond counts as 1 cloud. So this is my cheesy instructor-drawn version. Let's look at the computer-generated version now. And here's what I have. So here's the Lewis structure for COH2. And you can see, once again, there's a carbon-oxygen double bond. It does not matter if you draw the lone pairs like this right here, like at 120 degrees. I kind of had, I think, one on top and one on the right or something like that. It doesn't matter, all right? Just put the 2 pairs there. there with a double bond to carbon, and you're good to go. This molecule structure tries to show that that carbon is about 120 degrees, which is fine. You don't have to do that. So again, you could have like a carbon and a hydrogen straight up and one other one straight down, and oxygen like that, and that would be fine. All right, remember, Lewis structures don't really tell you anything, but VSEPR is what scientists use to do that. And here's the entry you would use in the Geometry Polarity Guide. 3 atoms, all right, in 3 clouds, no electron pairs. Everything around the carbon is not the same, so it's asymmetric. This one's going to be trigonal planar for both electron pair and molecular geometry. The angles will be 120 degrees. It's a polar molecule. In the Geometry and Polarity Guide, the first entry is electron pair geometry, and the second one is molecular geometry. You'll see that if you have the whole thing in front of you. I'm going to do one more example. This is a compound, sulfur, with 4 fluorines and 2 chlorines. And there's a couple different things about this one that I'd like to show you. So anyway, SF4Cl2. All right, well, let's go through the list. The first thing, figure out what the central atom is. Fluorine is the most electronegative of all. It will not be in the central part of the molecule. And chlorine is pretty high. It's one of the higher ones. So sulfur, this one, is definitely going to be in the middle part. Now, if you look here, there's 4 fluorines and 2 chlorines and 1 sulfur. So this is going to be a molecule where the sulfur is going to have an expanded valence shell. And normally, sulfur usually likes to try and have an octet, which is 4 clouds around it. But you're going to see on this one that sulfur is going to take on an expanded shell, which in this case means octahedral. You can only do octahedral and trigonal bipyramid if you have an element in the 3rd period and lower. Periods go left to right. Sulfur is part of the 3rd period, so sulfur can go beyond the octet, and in this case, it will definitely do that. So sulfur in the middle, fluorine around the outside. I'm going to draw this, and I'm just going to put the atoms around. Now, I'm going to put 4 fluorines around and 2 chlorines like that. And again, you can have any combination around the sulfur that you want, but that sulfur is going to be the central atom. Now, we need to figure out valence electrons. Sulfur is group 6. Fluorine is 7, and there's 4 of them. And chlorine is 7, and there's 2 of those. Remember, everything in the same group has the same number of valence electrons, which is kind of cool. So if you count this up, this goes to 48 valence electrons. And if you divide that by 2, that means you're going to have 24 pairs. So with the pairs, you have to connect the outer atoms to the inner atoms. So right away, I'm going to put a single bond between the middle sulfur and those outside ones. That's 6 of my 24 pairs. That means I have 18 pairs left to go. Now I'm going to try and put lone pairs on the outside atoms first, giving them an octet. And if there's any left over, we're going to put them in the central atom. So each of those atoms, fluorines and chlorines, can handle 3 lone pairs. 3 lone pairs plus a bonding pair is 4 pairs. That's the octet. And the outer atoms, you want to make sure that they get it. So I'm going to start on this fluorine and give it 3 lone pairs. That makes that fluorine happy. This is the 4th pair, 5th pair, 6th pair, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 pairs. So you can see that by giving out those 18 pairs, I used up all of my electrons. I don't have any for the middle sulfur, so we're good to go. So this is the Lewis structure for SF4Cl2. Woohoo! Again, same kind of idea as we've done in the other ones, we just have more electrons to deal with. And this is where counting your electrons will become super important. Sulfur in the middle has 6 bonds around it. So that's like 6 clouds. And 6 clouds, all right, means that you have 6 atoms, no lone pairs. So electron pair geometry here is octahedral. Octahedral is the name when there are 6 clouds around a central atom. You could have a lone pair or two, but as long as there are 6 clouds, you're going to have octahedral. Now, just like before, the molecular geometry is also going to be octahedral because there are no lone pairs around the central sulfur. The EPG and the MG will be the same. Now, this is where the geometry and polarity guide can be kind of handy. If you look at the angles, it says the angles for this one, like all octahedral, 90 degrees and 180 degrees. Let's stop there for a second. An octahedron has like a central atom, and there's essentially like a square of atoms around it. So again, remembering that I am the world's worst artist, okay, imagine that this is literally kind of flat. And these X's here, which I'm drawing, are like atoms in the plane. So the square I've drawn is literally the square on the screen of this video you're looking at. But octahedral also has an atom that comes out of the board. So I'm going to try and draw an X, and imagine that's coming out of the screen at you, which is really cheesy. A lot of times scientists will use what they call the wedge to try and show that, which is kind of hard. And then I'm going to use a dotted line here to show that there's also an atom then going into the screen. So if you can visualize it here, you've got an atom coming out of the screen at you, one going into the screen, deeper into the screen, and the X's and the square are like right on the screen. So we have a lot of 90-degree angles, all right? So for example, this angle right here would be 90, as well as this angle right here would be 90, and that's totally cool. But notice that it said 90 degrees and 180 degrees. If you look at the drawing that I did up here in the upper left, I would argue that the chlorine-sulfur-chlorine angle here is 90 degrees, okay? But in an octahedron, you can also have 180 degrees. So over here, let me redraw this structure. I'm going to put the sulfur in the middle, and I'm going to put the chlorines opposite each other. So when I draw the lone pairs and I fill in the fluorines, lone pairs, notice now how the chlorine-sulfur angle, 180 degrees. So sometimes the bond angles will help you to see isomers. And this molecule has an isomer. It's the same number of atoms, SF4Cl2, but there's 2 ways to draw it, all right? The way that I drew it up here first in green, that's the 90-degree isomer. And the way I just drew it over here in red, that would be the 180-degree isomer. So pay attention to those bond angles. You know, I'm not just making you look these things up for the heck of it, to waste your time. I'm trying to like show you something that could be really helpful. And you can a lot of times tell if there's an isomer in a molecule from the bond angle. And why this is so important. Your 90-degree version of the isomer up there, everything around this sulfur is definitely not the same, all right? And you don't have anything canceling each other out. The 90-degree one is a polar molecule, all right? But the interesting thing, in the 180 molecule, if you have atoms exactly apart from each other, and so the Cl's are 180 from each other, and even though I haven't drawn it very well, those F's are 180, and these F's are 180, those are canceling each other out. The electronegativity pull of the one fluorine is being canceled by electronegativity pull of the opposite fluorine. And the chlorines over here are canceling each other out too. So this molecule with the 180 isomer, non-polar. And that can make a big difference when it comes to reactivity. So the angles will help you to see the isomers sometimes, and then definitely you can then use that to figure out if something is polar or non-polar. The non-polar entry over there would be an asymmetric molecule because everything around the central atom is the same. The CLs are 180 from each other, so they cancel. The two Fs are canceling each other. But in the first version of the diagram I drew, you don't have that. The CL angle is 90 degrees. Nothing's getting canceled there. You have to have the same kind of thing opposite. This FSF angle right here would be 180, but the other angles don't. That's a polar molecule. This is now the computer-generated version for the same kind of thing, and maybe this will make a little bit more sense. Like before and stuff, start with sulfur, figure out the number of valence electrons, electron pairs, and you can draw them. Now, in later courses, when you have a chlorine-chlorine 90-degree angle, like right here, we'll call this a cis angle. And if you have a chlorine-chlorine 180 degrees like you do here, we'll call it trans. But don't worry about that for right now. I just want you to see that there are two isomers possible, and that's really important. All right. The polarity will make a difference. First of all, electron pair geometry, molecular geometry, octahedral for both, because you got 6 clouds, everything's around it and stuff like that. But the angles 90 and 180 hopefully give you a sense as to what's happening here. And in this molecule, you do have a choice. So the one isomer will be polar and the other isomer will be non-polar. The one with the 180 angles where things cancel out, that will be the non-polar one, and the cis one will be more polar. So this stuff becomes pretty important. All right, we're going to talk more about this definitely in future lectures, but hopefully you get the idea of what's going on. I'm going to show you a quick video now about how you can build these structures with a model kit. And if this was a face-to-face lab, we would actually be quote-unquote playing, well, I think of it as playing, it's not really playing, but we would be playing or building the molecules with one of these structure sets, and they're kind of fun to do. So watch this video and you can see kind of what's happening. This is the chemistry model kit. There's different versions of it, but they all have a lot of similarities. When you open the box, you can see there's like these multicolored little pieces, and they all represent different atoms. Usually black is carbon, white is hydrogen. Then there's usually different kinds of bonds. That's a single or sigma bond right there, and that's by far the most common. So let's build the CH4 model here. And you can see the hardest part sometimes is just getting the atoms, but lo and behold, this then is CH4, and CH4 is tetrahedral, and you can see with the model kit, it comes out really nice. Now we're going to build CH2O, but pay attention to the longer bonds. We're going to make a double bond with oxygen. You can use those longer bonds to make double or even triple bonds. So this is CH2O, and you can see the nice trigonal planar geometry you get out of it. It's actually pretty clever how they do this. You can also have triple bonds. This is ethyne. There's a carbon-carbon triple bond, again just flat along there. Now we're going to construct the SF4Cl2 molecule, and the silver one is the octahedral, the Fs are the green ones, and the Cls are the blues. And you can see quickly then how you can make one. This is the 90-degree isomer we talked about, but it's easy to flip them and make a 180 non-polar version, and that's kind of cool too. There's so much more you can do. This is carbon dioxide, again nice and linear geometry. This is the PF5 with a trigonal bipyramid center, so definitely there's a lot of utility for having a good model set. As a bonus, because you're still watching this video, I'd like to do a fourth example with you. I said I was going to do just 3, but now let's throw a fourth one in for the heck of it. And this problem has to do as well with isomers, okay? And isomers become really important for future lectures. Now, in this particular problem, there are 3 isomers of C3H8O. And the question is, how the heck do you start drawing them? Well, in these kind of problems, you have to remember, carbon and oxygen must have 4 bonds. All right, that's the octet, and there's no exceptions. And hydrogen can only handle 1 bond. So, for example, you won't see any kind of H kind of things because this hydrogen in the middle has too many bonds. You can only have 1 bond, okay? Another hint is that, as I mentioned briefly in lecture, and we'll talk about more, carbon really likes to have 4 bonds around it. And that can be 4 single bonds. It could be, for example, 2 single bonds and a double bond. You could even have a triple bond and a single bond, something like that. But carbon doesn't like to have lone pairs, all right? There are some exceptions to that, but generally speaking, you want to try and stay away from it, at least in Chem 222 and Chem 223. So when we're building structures with carbon, single bonds or 4 bonds total is what we're after. Now, oxygen also likes to have 4 bonds around it, and we're going to see that oxygen is happiest when it has 2 single bonds and 2 lone pairs, or as it did with that formaldehyde example I showed earlier, it can also have a double bond and 2 lone pairs. So we're going to be looking for molecules that have these kind of structures, all right? No hydrogens with 2 bonds, no carbons or oxygens with only 1 bond, for example. They're very, very set kind of pieces. What I would do on a molecule like this is a lot of these molecules have a carbon chain, all right? So I'm going to start by just drawing 3 carbons in a row like that. And you can see that there are a lot of hydrogens for the amount of other atoms we have. So let's start by just putting hydrogens all the way around the molecule. Now remember that carbon likes to have 4 bonds and 4 bonds only. I can literally do this kind of thing and put the hydrogens around the carbons. Cool, carbons all have 4 bonds. Hydrogen has just 1 bond. Awesome. But, I forgot the oxygen. And you can't be losing atoms in these kind of problems. So, alas, this structure won't work here, okay? However, let's erase the last hydrogen I put there. And I'll fix that hydrogen a little bit. And remember here that oxygen can have 2 single bonds. So you can literally put the oxygen in the middle and put the lone pairs on the oxygen. Well, this looks like a reasonable structure. We have all the carbons, the 1 oxygen, and 8 hydrogens. One way, though, to really make sure you've got a good structure is to go back and count the number of electrons. Now, I didn't even do that. I got so excited to talking about the different ways and that you can put these atoms around. But really, you should count the number of atoms. So carbon is group 4, and there's 3 of them. And we're going to add that to hydrogen, which is 1, and there's 8 of them. And oxygen is 6, and there's 1 of them. So if you count this up, let's see, 12 plus 8 is 20, plus 6, that would be 26 valence electrons, or if you divide by 2, that would be 13 pairs. So if you go back to the structure we drew earlier, I should have a total of 13 pairs. 1 pair, 2 pair, 3, 4, 5, 6, 7, 8, 9, 10, 11 single bonds. Lone pairs count 2, 12, 13. Bam! We have one of the 3 isomers, all right? This compound, you don't have to have red circles around everything, by the way. Sorry for the cheesy instructor tricks. This is one of the 3 isomers, okay? And I've distributed all the electrons. Carbon's got 4 bonds, no carbons with lone pairs. Oxygen, in this case, has 2 singles and 2 lone pairs, so it's happy. Hydrogen has just 1. Everything is good to go. Let me redraw that molecule real fast, all right? It's basically carbon, 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 OH, lone pair, hydrogen, 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 hydrogen. Okay, so that's a little bit better than the old one. The reason I wanted to redraw it is that in this molecule, the OH part is on one of the outside carbons, the far right, okay? Well, we can easily make another isomer if we put the oxygen between the carbons, all right? So what I did is I essentially took this oxygen and I put it in between these two oxygens right here. Now, if you do this, all right, remember that oxygen, if it has two single bonds, it likes to have two lone pairs. So I'm going to put two lone pairs on it like that. I'm going to put hydrogens around all of the carbons once again. And lo and behold, I now have 1, 2, 3, 4, 5 hydrogens on the left, 6, 7, 8 with the ones on the right, 8 hydrogens. Pretty sloppy there, sorry. 1, 2, 3 carbons and oxygen. If you count the electrons, still got 13 pairs. This is another one of the isomers, all right? And all I did was, instead of having an OH or a COH, I guess, in the first one, now we have a COC. Cool. The third isomer, all right, can happen as well, but I'm going to go back to the first drawing, which is this one right here. And you can flip the OH with the middle hydrogen, all right? And if you draw that, and I'll try and draw it down here, I've got 1, 2, 3 carbons, but now I have an OH sticking off that one, all right? So what that means is I'm going to have hydrogens all the way around the other parts. My oxygen still has to have two lone pairs. And if you count this up, this is also a third isomer. It's different than the first one because the OH was off the first carbon. This one, and the green one down here at the bottom, the OH is off the second carbon. So these three structures I've drawn, don't worry about that one because that's all. These three here, which are so sloppy, and I'm really sorry, I'll show you better examples. Those are all the three isomers. Now, if you drew a CCC and you put the OH off the end like that, H, 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 and you filled in all the bonds, it would look like this was another isomer, all right? But the thing is that as long as you're above absolute zero, these molecules are rotating and flexing and moving around like crazy. And this OH right here, if you were to totally flip the molecule around, it would become this molecule right here. So this one is not an isomer. If you can rotate the molecule left to right, and it's the same kind of thing, and that's what we would do, the one I crossed out. If I rotated the first one I drew left to right, it would become like the other one. That's not an isomer, so it gets a little crazy. So this is my super sloppy version, but hopefully you get the idea of the things to look for. If you use computer-generated molecules, it looks a lot better. Here are the three isomers. Don't be too worried about the names right now, all right? But the one on the far left was the OH off the end carbon that I drew first. The middle structure there is actually the one I drew third, the last one, so I apologize for that. And then the one on the far right is the one I drew second, where the oxygen in the middle are carbons. But these are the three isomers. And again, if you can just rotate one and it goes into another form, then those are the same. But I can't rotate like the first one into the second one. I'd have to physically pull the atoms apart to turn the 1-propanol into the 2-propanol, stuff like that. So try and have fun with it. Go through, always count the electrons, make sure you got them all and stuff. These molecules didn't have any double bonds, but sometimes you'll have a double bond O instead of a single bond O, or a ring structure, stuff like that. All things that you can do. Okay, that's it for the video. I hope this has helped you to kind of see what Lewis structures are all about, how to build them, and you should have no problem creating them yourself. If you do run into trouble creating Lewis structures or understanding VSEPR geometry, definitely contact me. I'm happy to help at any time. You can also talk to the LSC/Avid Center located above the library. They are also very helpful and have people up there that know what this class is like, so don't be afraid to reach out and stuff. It's totally cool. All right, good luck with your Lewis structures and have a great day.